Alright, what's up guys? In this video we're going to pick up some calculus here. This is going to be another integration practice video. This is going to be example number 38 of the integration practice series. Okay, so we're asked to evaluate the integral e to the 4x multiplied by sine of e to the x dx. So I think an appropriate thing here is to just start with a simple u substitution. And just take it from there. So we'll select u to be e to the x. The derivative of e to the x is just itself. So e to the x dx, you need to solve for the dx, so it'd be 1 over e to the x du is equal to dx. So what happens is you get the integral e to the 4x sine of u. It looks like it's going to be all over u du. Now we do see a little bit of a problem because we're now need everything in terms of u, and we still got x's flying around, as I've said before in plenty other integration videos. If you get into a situation like this where after you do the substitution, you still have the original variable that you were working with, and there's no way for you to get rid of it. There's no way for you to convert, in this particular case, x in terms of u. Then you probably picked the wrong technique and you need to try something else. But that isn't always the case. If you look here at our integral, notice here that u was e to the x. Okay. So what we need is we need to get x here in terms of u. So what we can do is take the natural logarithm of both sides so that we can solve for x. Okay? So we'll take the natural logarithm of this side, the natural logarithm of this side, and essentially solve for x. So remember, ln of e to the x is just x. So this would be x is equal to ln of u. So now the integral becomes e to the 4 ln of u multiplied by sine of u all divided by u du, and we can simplify this down to the integral u cubed multiplied by sine of u du. Okay, so now we need to integrate this. So hopefully you can tell that to get the final answer to this, we're going to have to apply integration by parts 3 times, because every time we do integration by parts, it's just going to reduce the degree of this u here. So not something that's overly difficult, but just a bit lengthy. And I think there's a difference between an integral that's difficult and one that's lengthy. It's very important not to assume that just because an integral is lengthy that it's somewhat difficult. It's just lengthy, and some integrals are just going to take a little bit of time to get through, but go with the standard techniques that you know how to do when you're dealing with these types of integrals, and keep going with it. And again, integrating something like u cubed sine of u du, although it's going to require integration by parts 3 times to get the answer, it's not something, if you've seen any of the videos that we've done in the past, that we haven't solved stuff like this before. We certainly have. And so let's do that. So recall that the integration by parts formula is the integral of u dv is equal to uv minus the integral of v du. So we need a u and we need a dv. Now, this may be a good candidate for tabular integration. If you don't know what tabular integration is, it's a kind of another way to do integration by parts. The only problem with tabular integration, can't be used all the time, whereas with integration by parts can always be used, even if it takes a minute to get through most of the process. So there are some cases where you can use tabular integration. Me personally, although I do know what tabular integration is, I've never really used it all that much, so I can't say that I'm very great at the technique itself. So I would much rather just do it the long way. But tabular integration does work in some cases, but it doesn't work all the time. And it's kind of like, if you remember from college algebra, You know, there's polynomial long division and then there's synthetic division, but synthetic division can't be used all the time because we need to be dividing by a linear term. Whereas with polynomial long division, I mean, that can be used all the time. Maybe it's not the quickest way to do it. Maybe it's not the easier of the two methods, but it can always be used. And that's pretty much the same case here. Integration by parts, it might take a little bit more work to do it multiple times, but it can always be used, whereas in tabular integration can't be used all the time. So I've done my selections for U and dv, and quite frankly, neither of these is harder to differentiate or integrate than the other. So we're just kind of going through and doing all of this. Okay. Also, for tabular integration, you have to remember, just kind of give you a little input on that. For tabular integration, basically what you're doing is you're creating like a table, and the U that you pick, what a lot of people don't know about tabular integration, you need to be able to take repeated derivatives of the U and eventually get to zero. If that doesn't happen, then you either can't use tabular integration or you can switch your U and dv selection and try it. But if that doesn't work, then you can't use tabular integration. So whatever you pick your U to be, you need to be able to take repeated derivatives and end up getting to zero. If that's not the case, even after you switch it, you can't get to zero, you can't use tabular integration. So it's just one of those things where it just can't be used all the time, and it's just a hassle. So let's continue with integration by parts. So this would be negative U cubed cosine of U. We're going to get two negatives to make a positive, so I'm going to pull the 3 out as that's just a constant. And then, as I mentioned to you, we're going to have to apply integration by parts a second time here. And hopefully you're seeing why, because now we're down to the integral U squared times cosine of U du. So all applying it once did was just drop the degree of the U. And these are some notable examples of when you may have to apply integration by parts one time or multiple times. So if I see something like x squared times e to the x dx, that'll require integration by parts twice. Something like the integral ln squared of x will require integration by parts twice. Something like, I don't know, ln squared of x all over x squared, that'll require integration by parts twice. So there are some notable examples where you can easily tell where the technique needs to be applied more than once. So let's do it again. We're not going to deviate really from the selections that we had from the first one to the selections that we are doing now. We're going to kind of stick with it. And like I said, nothing that we're doing here is difficult, but it is a bit lengthy. So we're going through and we're making our selections for U and dv. I just took the derivative, antiderivative of cosine is sine. So remember, there was a positive 3 that was pulled out. The crazy thing, I don't want to say crazy thing, but the very important thing to do, and you want to always make sure you're doing this, be very neat with your math work, but you definitely want to make sure you're being very neat when you have to apply integration by parts multiple times, because you're going to have to go back and kind of attach everything together. So you should be, being neat anyway with your math work, but definitely when you have to use this method more than once, because you're going to have to go back and get the information. So again, the 2 can be pulled out, and so it's going to be a minus 2. And again, we're going to have to do integration by parts one more time here. Hopefully you are seeing why. Because now we're down to the integral U times sine of U du. So hopefully you're seeing why we have to apply it multiple times. So all it did was just reduce the degree of the U every time we actually did it. Which, in other words, if we wanted to do, let's say, this integral U raised to the 99th power times sine of U du, you could do it with integration by parts. I would assume you wouldn't want to do that by hand. Put that into a computer system and let a computer do that. But if you really want to do that by hand, you would have to do it 99 times before you actually got it simplified down to the point where you can get your answer. So Again, everything is really going well. We're not doing anything overly difficult here. So let's continue with the process. So I'm just taking my antiderivatives here, and we're kind of going through the whole process. And as I continue, now I didn't forget about the fact that there was a -2 that was on the outside that was a constant. So we'll end up with negative u cosine of u. And two negatives make a positive, so this would be plus the integral cosine of u du, which is going to give us a positive sign. So when we integrate it, of course. So this would just be -2 negative u cosine of u plus sine of u. Okay. So now we're pretty much done with our application of integration by parts repeated times. Now we got to attach everything together. So we have to go back to the first integration by parts, but also not forgetting about the fact that we did start with a u substitution. So again, this one is a little bit of work to kind of track. So if we combine everything together, it looks like we'll end up with negative u cubed cosine of u. Remember, the 3 was positive. I'm going to expand everything out in a minute, so once I put the u back in, so don't worry. This was sine. This was -2, and then it was negative u cosine of u plus sine of u. Now, if you go back to substitution at the beginning, remember that u was e to the x, so we got to put that back in there. But we're going to have to do some simplification, okay? So we want to make sure that we're doing this. So we'll have negative, this would be e to the x cubed. We're going to have to simplify that. That's going to be e to the, well, it's actually going to be negative e to the 3x, but don't try to do too many things at once. So all I'm doing is just plugging the original substitution back in, and we're going to simplify it here in just a minute. So it looks like we'll end up with e to the x squared, which it's going to be e to the 2x, and we'll have sine of e to the x -2 negative e to the x cosine of e to the x plus sine of e to the x. And all I'm doing here is just substituting everything back in. Alright, so let's simplify this a little bit, and we'll take it from there. So if we simplify this side over here, forgetting about that side right now, we'll simplify that side, but let's just go ahead and expand out this side over here with the 3. So if we expand that out, we'll get 3e to the 2x times sine of e to the x. If I distribute in the 2 negatives make a positive, so this would be plus 2e to the x multiplied by cosine of e to the x plus sine of e to the x. Okay. What am I missing? I'm not missing anything. All right, so if we go back, so we can actually just go ahead and write our final answer down, actually. So our final answer all right, so we're asked to integrate, what was it? E to the 4x sine of e to the x dx. So the answer is going to be a little long. So it looks like we'll get negative e to the 3x cosine of e to the x plus 3e to the 2x sine of e to the x. This would be plus 2e to the x cosine of e to the x. We do have to multiply by the sine part. I did forget that part up here. So actually this would be 3e to the 2x sine of e to the x plus 2e to the x cosine of e to the x. And we do got to multiply it by the sine, so this would be plus 2 sine of e to the x. Sorry, I forgot about that part, so we'll do it here. So this would be plus 2e to the x cosine of e to the x. And this would be plus, well, it'd actually be minus, because we got a negative sign there. So this would be minus 2 sine of e to the x, and then we do got to add a plus c. And that would be the solution. So a bit of a long answer, but nevertheless it's the correct one. Alright, so let me know if you have any questions about how I got my solution. I'll be more than happy to share it with you. Alright, I will see you guys next time. Y'all take care.